Okay, so today we're going to prove Heron's formula, which states that the area of any triangle ABC is given by the equation. So the area is equal to the square root of the semiperimeter times the semiperimeter minus A times the semiperimeter minus B times the semiperimeter minus C, where of course S is equal to the length of A, which is opposite of angle A, plus the length of B, which is opposite of angle B, plus the length of C, which is opposite of angle C. All right, so let's go ahead and start this proof. So first off, we're going to draw altitude BD and let H equal BD. All right, so let's draw our altitude. We're going to call that BD, and then this will be called H. All right. So we're going to be looking at here, sine of C is equal to opposite over hypotenuse, H over A, since this is a right triangle from this altitude. And this implies, of course, if we multiply both sides of this equation by A, we'll get H is equal to A sine of C. Okay, so now we're going to dive into the area of this triangle. So we know that the area of triangle ABC is equal to 1/2 the base, which of course in this case is B, right? Let me move this B down a little bit. The base, right, times the height. But now we have a different form for our height. So this is equal to 1/2 base times A sine C. Or we can rewrite this as the area of triangle ABC is equal to 1/2 AB sine of C. All right, so now what I'm going to do is I want to get rid of this fraction, so I can multiply both sides by 2. Okay, so this, I'll have 2 times the area of triangle ABC is equal to AB sine of C. And now what I'm going to do is I'm going to square both sides of this equation. So I'm going to square 2 times the area of triangle ABC, and I'm going to square AB sine of C. All right, so this will give me, so this is 4 times the area of triangle ABC squared is equal to A squared B squared sine squared of C. All right, so remember the Pythagorean identity. So we'll do a little box here. So recall, recall Pythagorean identity, which states that sine squared of any angle, right, plus cosine squared of any angle is equal to 1. So if I were to manipulate this equation, I could get sine squared of any angle is equal to 1 minus cosine squared of any angle. So I'm going to use this here. Okay, let me scoot down a little bit. So this implies that 4 times the area of triangle ABC squared is equal to A squared B squared 1 minus cosine squared, not theta this time, right? It's C in this particular case. C, right? So now I'm going to use a law of cosines. So recall that the law of cosines. Okay, so remember C squared is equal to A squared plus B squared minus 2ab cosine of c. So what we're going to do is we're going to solve for cosine of c and then plug it in over here. Okay, so let me draw a little box here. I don't know how far it's going to go. Let me just draw this right here. Okay, so what I can do is I can add 2ab cosine c to both sides, right? And subtract c squared to both sides, right? So if I do that, I would have 2ab cosine of c is equal to a squared plus b squared minus c squared, right? And then if I want to solve for cosine c, I can divide both sides of this equation by 2ab. So this gives me cosine of c is equal to a squared plus b squared minus c squared all over 2ab. So that is my cosine c from the law of cosines. And I'm going to plug it into my equation here. So I have 4 times the area of triangle ABC squared is equal to a squared b squared times 1 minus, and this is cosine squared c, right? So it'll be a squared plus b squared minus c squared all over 2ab, and that is squared. All right, so now let's go ahead and do this squared, right? This times this. So this implies that 4 times the area of triangle ABC squared is equal to a squared b squared times 1 minus. So remember, with fractions, we multiply straight across. So a squared plus b squared minus c squared times a squared plus b squared minus c squared would just be this squared, right? I'm just going to leave it exactly like that. Right? But the bottom, I'm actually going to do, because it's a little easier. So 2ab times 2ab would be 4a squared b squared. Right? So now I'm going to distribute this a squared b squared to both of these terms, right? So this implies that 4 times the area of triangle ABC squared is equal to a squared b squared. And look, a squared over a squared, that turns into 1. B squared over b squared turns into 1. So what I'm left with is a squared plus b squared minus c squared squared all over 4, right? Okay, so now what I'm going to do is I'm going to multiply both sides of this equation by 4 so I can get rid of this fraction, right? Okay, so this implies 16 times the area of triangle ABC squared is equal to 4a squared b squared minus, and then of course 4 times this fraction would just leave us with the numerator, a squared plus b squared minus c squared squared. All right, so now I'm going to focus on the right-hand side. So this equals means that I'm just focusing on the right-hand side. Notice that this is actually a difference of squares, right? So the first one would be 2ab, and then minus a squared plus b squared minus c squared, right? And then 2ab plus a squared plus b squared minus c squared, right? This is the difference of squares. And now I'm going to distribute this negative. This will be, and reorganize it in a way that'll be nice. So negative a squared and then plus 2ab, right? And then distribute the negative to b squared, so that'll be minus b squared. and then distribute that negative, so that'll be plus c squared. And then this will be a squared plus 2ab plus b squared minus c squared. All right, so the reason why I did this is because, well, first, I will factor out the negative from these three terms, okay? So negative a squared minus 2ab plus b squared, and then plus c squared, right? And here, this is the trick I'm trying to use. I know a squared plus 2ab plus b squared is the same thing as a plus b squared, right? Because remember, a times a is a squared, a times b will be ab, and then b times a is ab, so there will be two ab's, and then b times b is b squared. So this is equal to this, and look, I have another difference of squares, and I'm going to get one over here too. So this is equal to, so this is c squared in front, minus, and then of course, a squared minus 2ab plus b squared is the same thing as a minus b squared, right? So a plus b squared minus c squared, right? Because a times a is a squared, a times negative b is negative ab, negative b times a is another negative ab, so there will be two negative ab's, and then negative b times negative b is positive b squared. So this line is equal to this line, and I'm going to use the difference of squares again, so equals. So this one, this difference of squares will be c minus a minus b, and then c plus a minus b. So that's this first difference of squares. And then the next one is going to be a plus b. Let me put another parenthesis right there. Minus c. And then a plus b, another parenthesis, plus c. All right. Let me make this a little bit more nice. Okay, so here, and then there's my parenthesis. All right. So now this is equal to, so c minus a minus b, we'll distribute that negative. So this will be, negative a plus b, right? Distribute that negative, and then plus c. So that's my first one. My second one will be a minus b plus c, right? My next one will be a plus b minus c. And then my last one will be a plus b plus c. All right. So now I'm going to remember my formula calls for the semi-perimeter, right? So I'm going to draw a little box here. So the semi-perimeter, right? Semi-perimeter is S is equal to A plus B plus C over 2. Now notice I can get A plus B plus C in all of these doing a little bit of a manipulation, which I'll do in a second, but I do have this A plus B plus C here, right? So if I were to solve for A plus B plus C by multiplying both sides of this equation by 2, I would get 2S is equal to A plus B plus C, right? So I'm going to show you how I'm going to get A plus B plus C in all of these. So this is equal to, so would you guys agree that if I were to write A plus B plus C, then I would have to subtract 2A, right? Because A minus 2A is negative A, right? And I'm going to use the same trick. I'm going to have a plus b plus c, and then minus 2b. And then I'm going to have a plus b plus c minus 2c, and then that final a plus b plus c, right? So now, wherever the a plus b plus c is, I'm going to substitute 2s. So this is the same thing as 2s minus 2a. This will be 2s minus 2b. And this will be 2s minus 2c. And then, of course, this will be 2s. All right. So in each of these, I can factor out a 2, right? So this is equal to 2 times s minus a times 2 times s minus b times 2s minus c, and then of course times 2s. So 2 times 2 is 4, times 2 is 8, times 2 is 16. So this is equal to 16 s minus a. Well, actually, I'm going to move the s to the front to fit my formula, right? So it'll be s times s minus a times s minus b times s minus c. And remember, I had 16 times the area of triangle ABC squared is equal to all this junk, right? So I know, so this implies that 16 times the area of triangle ABC squared is equal to 16 times s minus a times s minus b times s minus c. So if I divide both sides of this equation by 16, I get the area of triangle ABC squared is equal to s times s minus a times s minus b times s minus c. And then to get the area of triangle ABC without the squared, I can take the square root of both sides. And of course, since everything is positive, I only have to worry about the positive value, right? So this implies that the area of triangle ABC is equal to the square root of s times s minus a times s minus b times s minus c, which is Heron's formula. That is exactly what I tried to prove. And that is the proof of Heron's formula.